All right, so here we have part 2 of my analytical techniques videos. And for this, I'll just start like it's a direct continuation from the last one. All right, so part 1's already posted, and now perhaps you're looking at part 2 right afterwards, okay? All right, now, so then first thing I noticed about this limit, that if I tried to do this by plugging in 0, it wouldn't work for me because I get this form of 0 over 0. Okay, so if I tried to do this limit by just plugging in wherever the x is going, 0, it just doesn't work. Okay, some limits you can do that way, but this one's not one of them. So this was a cue to do something, right? Whenever we're in this situation right here, there's something specific that we do. We reduce, right? Using algebra, we find some way to reduce that, and then we'll reapply the limit, hopefully with better success, to whatever we get. All right. So okay, I'll figure out some way to reduce this with all that I've learned in algebra, whatever that may be in this problem. Okay. So what I think will be useful for this one is to multiply this out and combine whatever like terms I can. Okay. So when I look at x plus 2 squared, that's x plus 2 times itself. So that ends up being x squared plus 4x plus 4. Okay. And then minus 4 over here. All right, so that's the first thing I would do. Now adding the like terms. The only like terms are 4 and negative 4. So I'll get x squared plus 4x, because those cancel, right? And then next I realize that there's some canceling with the x's I can do. Do I cancel those? No, I don't cancel those. I can only cancel things through division that are multiplied. So I factor out an x. Okay. Is that right? Yeah, if you multiply this back out, that's going to be x squared plus 4x, so that's correct. And then these cancel, right? And we're just going to get x plus 4. Okay, now it's reduced. I can't imagine reducing it any more than that. So now we'll reapply the limit to this, right? We were in the beginning going to figure out the limit as x goes to 0. But I'll apply that to x plus 4. And then here I can plug in the 0. If the x is going to 0, I can push it all the way there to 0. And I have no problems plugging that in and getting an answer, right? It says 0 plus 4 if x goes all the way to 0. And 0 plus 4 has an answer, and it's just 4. Okay? All right. So real quick, I'm done with this one. That's all I need to show you about it. I'm kind of nervous though. I see people all the time canceling the x's like this. All right, like just crossing those out. And I want to say you can never cancel things that are added or subtracted that way. All right. So in order to show you what I mean, let's do this. Let's say is 7 plus 3 over 3 equal to 7 plus 1? And here's what I'm trying to say. You see the 3 there and the 3 there? I think so many students are tempted to just say, oh, I get to cancel the 3's because there's a 3 on the top and there's a 3 on the bottom. And 3 over 3 is 1, so it's 7 plus 1, so it's just equal to 8, right? That's kind of what I'm afraid somebody would do up there with their canceling. Can you do this? Well, all right, let's see. If you do it this way, you're going to get 8, right? But what is 7 plus 3 divided by 3? It's 10 over 3. And is 10 divided by 3 equal to 8? Not even close. No, it's not equal to 8, okay? So, no, you cannot cancel in this case, all right? Can't do this. I wrote it down. It hurts to even write that down. Okay, but I wrote it down just to make a point that you cannot do that, because we can all agree that 10/3 is not equal to 8, all right? So any similar situation to that, like here it says x squared plus 4x. No, you cannot just cancel the x's here and here. You can't do it. All right. Okay, so there, I've established that. Now, what could you do? Well, if you had 7 times 3 over 3, yeah, you could cancel the 3's there because here it's multiplying and there it's dividing. And aren't you just going in circles? If you took 7 times 3 and then you turned around and divided by 3, you'd be right back where you started at 7. That's why we can cancel the 3's. And if you want verification of that, then you could say, well, what is 7 times 3? That's 21. And what's 21 divided by 3? Well, that is, in fact, 7. So this is definitely okay, and this is not okay. All right? I scratched it out. I don't even want that on paper, really, but I had to write it there just to show you that as tempting as that might be, you can't do it. All right? Okay. So let's look at another one, and I think this will be the last limit type problem we need to do. This says, what is the limit as h goes to 0 of f of x plus h minus f of x over h, given that the function f of x is 1 over 3x? So here, I would notice that no matter what that function is, this is going to be 0 over 0, isn't it? Like if you say, all right, h goes to 0, all the way there, it goes to 0, it is 0. Then what's this going to be? F of x plus 0, well, that's just f of x, minus f of x, well, that's 0 on top. And if h goes to 0, well, that's 0 on the bottom. So no matter what the function is, that's 0 over 0. So we're going to have to reduce it, all right? So I need to take this, and this here is called the difference quotient, and it'll have important relevance for us later on. For now, I'm just going to show you how to work with it. I got to figure out what this is for that function in order to reduce it. Okay? All right, so of course, like when we write our function notation this way, that's the thing that we're plugging into the function. If you wanted to, you could look at a function like that the x was just the spot where the input went. All right? And if you're going to plug in x plus h, it goes in that little box right there. I could think of functions like that. All right? If I wanted to, if it helps me, I can do that. The x is just a place where the input goes. In a function, you put in an input, you do the math, and you get an output. All right? So if I say f of x plus h, the x plus h is going in there. So that's going to be 1 over 3 times the quantity x plus h, all right? And then it says minus f of x. Well, f of x is right there. That's what you get if you put x in to the input, all right? So that's 1 over 3x and over h. Okay, so now can I reduce this somehow? Well, so remember, you learned some algebra. You learn how to factor, you learn how to add, subtract fractions, you learn lots of stuff in order to get to calculus. And what I can see with this one is that I could subtract the fractions and possibly reduce it. So I'll give you a real quick analogy. I like analogies. So it's kind of like this. Like what's 1/6 minus 1/4 over 2? It's a lot like that, okay? That I could find a common denominator between these. It happens to be 12. I'll multiply by 2 and 2, so that's going to be 2 over 12. And then I multiply by 3 and 3, so that's going to be 3 over 12. And then now that these have a common denominator, I can combine them. I'll get 2, take away 3, which is negative 1 all over 12. And then how do you take negative 1 over 12 and divide by 2? Well, when you divide fractions, you multiply by the reciprocal. So I'll look at this like negative 1 over 12 divided by 2 over 1. And that's going to be negative 1 over 12 times the reciprocal of this, which is 1 over 2. So that's negative 1 over 24. So that's the whole procedure if you want to see it. I think we can do something like this on that one though. Okay? We can get a common denominator. And we can subtract, and we can divide, and we can reduce like that. We don't really have any other options with that one besides to do it that way. So common denominator is going to be 3 times x plus h. So here's what I'll do. See this first fraction? I'll multiply by x over x. What is that number? That's 1. That's okay. You can multiply by 1. It's going to be the same. That's why when we get a common denominator, we always multiply the top and bottom of the fraction by the same number, because I need to keep that number the same. Obviously, if it's different all of a sudden, I'm not doing the same problem anymore. And with this next one, I'll multiply by x plus h over x plus h, which is again 1, because I need to keep it the same. We wouldn't want to multiply by anything different than 1. Now, if I do that, I'll get a common denominator of 3 times x plus h between these, and that was the goal. This thing down here I'll leave alone, h. Okay? All right, so let's see. I'll get x over 3x x plus h minus x plus h over the same thing. That was the point of getting a common denominator, that they would be in fact the same. So I'll get like that. And then I'll subtract these. What's that going to look like if I do that? I got to take this minus all of that. Okay? So my common denominator, 3x, x plus h. And then x take away this, all of this. So it's going to look like that. Okay? All right. We're getting closer. We're getting there. So the x's cancel. I get a negative h over 3x x plus h all over h. Now, I said it would be like this one. And it is like that one. We're to this point now where we're dividing. I want to take, if it's easier for you to see this way, I want to take this fraction and divide it by that one. And so how do you do that? Well, dividing by a fraction is equivalent to multiplying by its reciprocal. So let's do like this. We'll say we get negative h, 3x, x plus h, times the reciprocal of that, which is 1 over h. All right, so we'll get what? After some canceling, that's multiplication there. So I got an h on the bottom and h on the top. I'll get negative 1 and then 3x, x plus h. Okay, now I cannot do anything else to this. I've done everything I can. It's reduced, all right? Okay, so it is done. Let's reevaluate this limit, okay? So in the beginning, I was going to try to do the limit as h goes to 0. And I will attempt it on that. And if h goes all the way to 0, if I let h be 0, then I don't have any problems with what this gives me, okay? It would look like that. It would look like negative 1 over 3 times x plus 0. It would look like this, and it would be negative 1 over 3x squared. Okay. All right, so we got that one. There is definitely some algebra for you to know. If it's a little bit easier for you to think about it with actual numbers, maybe numbers are easier for you to think about than x's and h's, then think about it with numbers if you want to. I'll often show things with numbers instead of letters, okay? Just to help you out like that. But there's some algebra you might have to do a little bit of reviewing, okay? And if you need help on that, you could just ask about it. Now, I'm done with my techniques here. I need you to think of some philosophical questions, all right? Because really, when you do this, you don't have to understand what you're doing. Like, you can almost just memorize it. Okay, I multiply like this, and then I subtract, and I cancel, and like without even thinking about it, you don't have to know what you're doing, all right? It's not like you really have to understand some deep concepts or anything like that. But when you do math, there are concepts, and there is a lot to understand. And I need to get you to the point where you can understand what's happening, or you understand the concept, or you really know what's going on. It's harder to do that for most people. For most people, it's easier to do math than it is to understand what they're doing, okay? But I need you, as much as possible, at least I need to give you the chance to understand it as much as possible. So I want to talk about, like, why sometimes can you not plug in the number to get the limit, but then sometimes you can. All right? Here, could I do this limit by plugging in the 0? Doesn't work. You can't do it. Can I do this one by plugging in the 0? It does work. Okay, so I'm going to try to get you to understand why it works, why you can do that sometimes, not the others. So here it says, is the limit as x goes to 2 for some function f of x equal to f of 2? And when I say f of 2, I'm just saying, like, you take that function and you plug in the 2, all right? Can you always do limits by plugging in the number that x is approaching? And the answer is no, you can't always do it like that, okay? If, like, say for this one, the limit as x goes to 2 for x squared, yeah, you can plug in the 2 for that. If you plug in 2, you get 4. What do you think 1.9999 squared is? It's about 4. And what do you think 2.00001 is squared? It's about 4. So yeah, if x is really close to 2 for the function x squared, the y will be really close to 4. Okay, so for that one, yes, you can plug in the 2. I know that when we first learned about limits, I said that's an arrow, not an equal sign. And technically, this means that the x is not 2, but it's extremely close. Where's the y going to be? In the case of this function, plugging in 2 will tell you that. All right? But what about this one? Say you take the limit as x goes to 2 of f of x, where f of x is this piecewise function. It's the function x plus 2 if x is not 2, and y is x plus 2 if x is not 2, and y is 5 if x is 2. How would we even conceive of what that is? Well, draw the line x plus 2, but leave off the point where x is 2, meaning leave off the point where x is 2 and y is 4. Okay? Right? What would that give you if you put 2 in? It'd give you 4, but you got to leave that point off, so notice that it's an open circle. All right? Okay. And then, when x is 2, then y will be 5, so we get that point right there. So in this case, the limit as x goes to 2 is not simply what you get when you plug the 2 into the function. When you plug 2 into the function, you get 5. Right? And that's not the limit as x goes to 2. Why is the limit as x goes to 2 equal to 4? Well, if you look at the graph, and I said, like, that's an arrow, not an equal sign. It means if x is extremely close to 2, where's that going to put the y? Well, all these numbers, extremely close to 2, 2.1, 1.9, 2.01, 1.99, whatever, they're going to put you here or there, right in the neighborhood of what number? 4. That's why the limit's 4. So here you can't find the limit as x goes to 2 just by plugging 2 in. What's the difference between these then? It's that this one is continuous. There's no holes in the graph. There's no displaced points. There's no gaps in the graph. And this one is not continuous. Okay? So here's how it works. If you want to do the limit as x goes to a, whatever the number a is, you can plug in that number a in order to do the limit. If the graph of that is continuous at a, meaning there's not a hole there, there's not a point that's missing, there's not a point that's displaced, there's not a break in the graph, anything like that. That's when you can do the limit by plugging in the number. If the graph was not continuous, then you can't do it that way. and you have to look at the graph to figure out the limit, or make a table to figure out the limit, okay? All right, so that's the case where we can evaluate the limit by plugging in the number. All right, so that's one kind of, I would say, philosophical question, a question that requires you to think a little bit about it, let some concepts sink in, and so on. Next thing I want to, that's sort of like that is going to take some thinking and understanding on your part, is for you to realize the difference between these two functions. What's the difference between f of x is x squared minus 4 over x minus 2 and g of x is equal to x plus 2? Well, they certainly look different. I wouldn't say that this one has much resemblance to that, but what is the difference? They differ only at one single point. These are actually almost identical. They differ only at the point where x is 2. So how am I justified in saying that? In the other, I think it was the last video I made, I reduced something like this. Okay? So yes, this does reduce. I can take that, I can reduce it as x plus 2, x minus 2. And then I can cancel the x minus 2's and get it to be x plus 2. Can I really do that though? Does this simply reduce to x plus 2 and that's it? Or is there some fine print? Does this formula give you the same answer as that one all the time or not? Well, when you put 2 into this function, it's undefined. But when you put 2 into this one, you get 4. So no, they don't agree. They don't agree at 2, right? So you could reduce this to that only if the x wasn't 2. That's undefined at 2. Okay? So let's look at both of these. I want to look at both of them together so you can see the difference. Okay? So here is the graph of f of x. That's this one. That's x squared minus 4 over x minus 2. And I want to look at the other graph side by side with it. Okay? So that is g of x equals x plus 2. Okay? So this one is the same as that line, x plus 2, but I can include the point where x is 2. Okay? So it's just like x plus 2, but I gotta leave that point off. What point am I leaving off then? What if you put 2 into that? What would you get? You get 4. Well, you gotta leave that off. Okay? So it's gonna look like this. It's going to have a hole in it right there. 2 for x, 4 for y. I know my scale is not right, but I'm just trying to get you to see the picture. Okay? All right. So that's what this one looks like. What does this one look like? Well, that's just a line. There's no points are missing or anything like that. It's just like this one, except for it has that point on it right there. So it's going to look like this. Okay? Where, you got 2 and you got 4, and that point's on there. Because, in that formula, you plug 2 in for x, you get 4 for y. Okay, so do you see the difference between those? The only difference is this one is that one with this point missing. All right? Okay, now, so say we'll let that sink in a little bit. Why is the limit as x goes to 2 f of x, so that function, equal to g of 2? Okay. How come you can figure out the limit as x goes to 2 for that function there by just putting 2 into this one? Well, because, see the graphs? That's the only difference between them. If I wanted to figure out about where are these points, what am I going to get with 2.1 or 1.9? Well, this one shows me that when you put 2 in, you get 4. So it shows me that all those points are about at 4. It gives me a way to figure out the limit by just plugging in 2. All right? So that's something for you to think about. Right? You can tell the difference between them. That you can, based on that difference, understand why we can do the limit as x goes to 2 for this function by just plugging in 2 for that one. Okay? That's the kind of stuff that I want you to start thinking about. It might take some time to let it sink in, but that's your journey with math will probably be like that. It takes time to understand things. It's easier to learn to do them. It's a little harder, I would say most of the time, to actually understand what's happening.